substitution. So these are all come under, if it's not in the tables, you try and rewrite it. If the rewriting doesn't work, you do a W substitution. Now I'm going to cover it to as revision. It might be possible to do the exam without doing this. I need to cover myself just in case though. I don't know. There's definitely questions. So some of them that you can multiply out, but they're easier done with a W substitution. So I will show you, and you will need it if you go into level 7. Right. So if you've any rule of differentiation, you can run it backwards to get a rule for anti-differentiation. So for example, we have the chain rule. It says that the derivative of, I'm going to write this a funny way, the chain rule a funny way, v of w of x. Now the symbols don't really matter, the only thing that's important is v is the outside, w is the inside. So the chain rule says you differentiate the outside, so you get v dashed, evaluate it at the inside, and I'm just going to write w, times the derivative of what's inside, which I'll call w dashed of x. So that's the chain rule, differentiate the outside, differentiate the outside, evaluate the inside, times the derivative of what's inside. We can write this the other way around. So differentiate that to that, anti-differentiate that to that. So we would get that the antiderivative of v dashed w times w dashed of x, anti-differentiate this with respect to x, you get v of w of x.
Could you do that with an actual? Could you do that now, just with a standard equation, so we can see the inside outside?
No, because it's no.
Because that kills me. Like how you know.
I know, but actually none of us do it like this.
Okay.
So I'm just building up the theory. This is a difficult pattern spot, so we don't do this with a. We don't do it. Okay. So what we do is what we do is we're confronted with something like this. And we will see examples. And what we do is we say, we've tried, it's not in the tables, because there's things multiplied together. We've tried manipulation and nothing worked. We have to try a W substitution now. So what we do is, we just say, we try and let W be something. Now, we will talk about how you pick the W down here, right? So, just say you do know where the W is. So you let W be this thing. Okay, so you're going to say, I'm going to write now here is W, I'm going to say W is W of X. Do you know what? An example will be needed here, okay. So you're going to have, we're going to have 3 examples here. So we're going to talk about why you can't do it directly, why there's no manipulation, you have to try a W substitution. And we're going to say the 3 ways that you pick the W. Actually, I have 4 ways to pick the W. So the first is the best, but probably the hardest. So you're confronted with something like this. We will have 3 examples, okay? Somewhere in there, you see a function and a multiple of its derivative. A function, multiple of derivative, let the W be the function. That's the first way. The second way is you see the function inside something else. That's the second way. The third way, the ate, I won't talk about that yet because we're going to see the ate later on. And the fourth way is just try something. And if it works, it works. If it doesn't, try something else. Okay. So we'll just, so we'll show this by example. Okay. So actually, how do you know it needs one? Well, in terms of the strategy, if you fail to find it in the tables and none of the manipulations work, you're going to try this. There's other horrible things that can happen, like called a back substitution, that won't occur for you. Right, so I have 3 examples here. Okay. So you're confronted with this. The first thing you do is something like this in the tables, and you look in the tables for a moment and it isn't. Now you might say x squared is in the tables, x cubed is in the tables, and 1, the antiderivative of 1 is x, but they're not added together, so you can't do them separately. You can't do them separately. In terms of manipulation, the only real thing that you could do is you could say divided by x cubed plus 1 is x cubed plus 1 to the power minus 1. So you could end up with I equal to, so you have x squared and you've got divided by x cubed plus 1, which is the same as x cubed plus 1 to the power of minus 1. So that's a rewriting. I haven't anti-differentiated. Does anybody think they have any more rewriting?
And multiply the thing together, like?
No, you can't. You can do something, but it just makes it worse. You can't multiply them out, no. There's no, it doesn't. You basically can't because of this power. It just doesn't make any sense. I'll show you what you can do, but actually it doesn't work. So you could, strictly speaking, do this. Bear with me now. You could write the x squared, x cubed plus 1 to the power of minus 1. You could write this. This doesn't work. I shouldn't really show you this because it doesn't work, but I'll show you it anyway. So this is x to the minus 2 all to the minus 1, x cubed plus 1. And then when you have this, so this is like ab all to the n is equal to a to the n, b to the n. When they both have the same power, you can multiply them. So we multiply this in, and we get x to the minus 2 by x to the 3. What happens when you multiply like powers?
Add them.
Add them. So minus 2 plus 3 is 1. So x to the 1 plus 1 by x to the minus 2, you get this. And you've entered a whole world of pain. That's worse. You can't. Actually, that'd be a great question if you're just given that. I think I would, well, maybe I could, but I think when I was in college, I'd be stuck on that one. Right, so it's making it worse. So we're here. There's no other manipulations you can do. You can't do them term by term because they're multiplied together. So now you have to do a W substitution. Right. So we're going to say there's 4 reasons to pick it. The first is, can you see within this somewhere a function and a multiple of its derivative?
Right.
I don't see any x in here. Oh, I do. Okay. So x and 1. So there is, you could say any of these x's is a function, its derivative is 1. You've got x and a multiple of x, there's a 1 there, and you do w is equal to x, but all it's going to do is just going to change all the x's to w's. You'll never do w is equal to x. Okay. Another go. So you're looking for a function and a multiple of its derivative in there somewhere. If you can't see it, that's okay. The next thing that you do is you see something that's inside something else. Got something in here that's inside something else? X. Say again?
X cubed inside the...
X cubed. Now what you do is you'll take the 1 as well with it. So that's a reason to take, it's inside to the power of minus 1. Now if I asked you what is the derivative of x cubed plus 1, what would you say? Which is a multiple of that. So you do have function multiple of derivative. So that's another to use it. Liate, which we'll talk about later on, also says do x cubed plus 1, and after that you're just chancing your arm. I don't know what else you could pick. I mean, you could do x squared, but you just end up with nonsense. So it's x cubed plus 1. So this is how it works. Now this is actually a revision. You might have done it slightly differently. Again, like you did the chain rule slightly differently. But I recommend do it this way. Okay. So what we're going to do is we're going to rewrite this. Now the x squared is going to sit. This is a w. And you got to the power of minus 1. And now what we're going to do is we're basically going to try and instead of x, we're going to try and do w's. Now we need to get a relationship between dx and dw. How can you get a relationship between dw and dx?
Differentiate W.
Differentiate w. So w is x cubed plus 1. So now we differentiate this. So dw dx. What is the derivative of x cubed plus 1? 3x squared. Now what you do is solve this for dx. So multiply both sides by dx. And you're trying to get dx in terms of dw, so how do you get rid of that 3x squared? I want to get dx on its own. How do I get rid of the 3x squared? Can do it.
No, can't see.
Can't see. Oh, sorry, shit. Divide by 3x squared. So you get dw divided by 3x squared. Now, I will say at this point, this is revision, but it is possible that you don't need this in the exam. Now, we're doing the fourth thing after this is parts, which is potentially more difficult, but you'll probably have more time on it, more examples. Okay, so the dx is dw divided by 3x squared. So this is the rewriting. Does anything nice happen here?
No.
Yes.
Suppose we can multiply W minus 1 with, I don't know.
No, there's something nicer.
Yeah, 2x cubes.
2x squares? What
Square
about?
sorry.
We can divide them up.
Yeah. What's x squared divided by x squared?
1.
1. Gone. Is this a 3?
No, it's 3 times x squared.
No, the x squared, they're gone. X squared divided by x squared is 1. Is this a 3, really? No, that's the one that.
Yeah.
It's a 1 over 3, which is a constant, so you can fix that. That can come out. So this is 1 over 3 divided by 3, same as a third. So this can come out. X squared divided by x squared is 1, that's gone. And we have w to the minus 1. Is w to the minus 1 in the tables? So basically, okay, sorry. What happens is, so you rewrite this thing. Does this look simpler than this? Simpler? Yeah, that's good. That's what the w substitution does. It simplifies it. And then, so you go back to the start. Is this in the tables?
Yes.
Yes, it is. What is it?
It's
Antiderivative.
yeah, x n plus 1 over.
Oh, we said it doesn't work.
Oh yeah, no,
It doesn't work.
natural log of x.
So it's natural log.
So
The minus 1 doesn't work. So maybe I'll just do one extra line here. So this is 1/3 1 over w dw 1/3, and antiderivative 1 over w is log. So log of absolute value of w. And then what you do is you're asked to antidifferentiate with respect to x. This has got a w in it. Any idea what you do?
Change of W for the X.
Change the w back to the x. So w is x cubed plus 1. And then there's a plus c as well. To antidifferentiate. So we'll do 2 more examples. So as I said, this is revision. I want to put it in there because I want direct manipulation, W substitution parts. But you might get away without doing this because we're going to do 2 more examples and it may not come up in our later on. Okay.
Can you do that for all product rules if you wanted to? Is that
No.
no?
So he sees a product. It says, will this always work? The answer is no. In fact, with you can differentiate anything. You can't antidifferentiate everything.
Right.
So some things you have to do numerically approximate. So all these are chosen to be able to be done. So if I change that to an x to the 4, can't do it. Okay. Alright, so add one, e to the inverse tan, this is a hard one, right? E to the inverse tan of x, all divided by 1 plus x squared. It's not in the tables. Do The only real manipulation is to say that this is divided by 1 plus x squared, so do 1 plus x squared to the minus 1. Any more manipulations about?
Not really.
Not really, yeah. There's nothing else you can do. Now this one in terms of picking the W is very difficult. So it really is, I'll be completely honest with you. So what would happen here for most people is they could try the 1 plus x squared and it just won't work. And so they go back and try the inverse tan of x. Okay? So we'll see, yeah, so it says there's only 2 good reasons. There was 3 the last time. So you've got inverse tan of x as derivative 1 over 1 plus x squared. So you've got inverse tan of x as a function. And its derivative is 1 over 1 plus x squared, which is it actually in there. You can't say inverse tan is inside something else because so is 1 plus x squared. So they're equal on that level. The Liate we'll see a little bit later on. The Liate we'll see later on will say you should try the inverse tan. Okay. The third way doesn't work great. Okay, let's see what happens here. So I think this is saying what happens if you try w is 1 plus x squared, I think. So the third way doesn't work well because there are 2 functions inside another. This is inside and this is inside. In this case you would just try 1 plus, you could try both of them if you haven't a clue and see what happens. We know we should try this, but let us try w is equal to 1 plus x squared to see what happens when it goes wrong. So you will have to differentiate this. You get dw dx is 2x. You will get dx is dw over 2x. Let's see what you end up with.
Why did you, or why do we get 1 plus x minus to the power of minus 1?
Where did that come from? So this is divided by 1 plus x squared. So positive powers are multiplying, negative powers are dividing. Divide by this once is power of minus 1. So if you run this through, now what? So the good thing that happened here was the x squared divided by x squared was 1 and it disappeared. You need that to happen. If that doesn't happen, it didn't work. So for example, this is picking the wrong w. This is picking the w to be the 1 plus x squared. You do the e to the inverse tan of x. This is the 1 plus x squared is w. You get dw over 2x. There's no x is disappearing. There's no x over x. So you've got the mix of w and x is bad and suggests you won't be able to do it. There is a possible thing that you're not going to do. You can do what's called a back substitution, where you write these x's in terms of w, and you can do that. You end up with this. This looks even worse than the original, and this is worse. So what you get to here and it didn't work. So don't do the 1 plus x squared. Try the inverse tan.
JP, if I got to there, I wouldn't know that it wasn't working.
Because you have x's and w's. X's and w's.
Yeah, no, I know, but you know the way you're saying this is a revision, it feels like brand new. I think we probably need to do a little bit extra on this rather than just a quick fly through, you know.
I haven't time.
Okay.
And as I said, you could get through the final exam without needing to do any w substitution. Okay. X's and w's it hasn't worked. So we'll try the w is inverse tan of x. So we'll rewrite. We had e to the inverse tan of x. Inverse tan of x is w, so that's our e to the w. We also had the 1 plus x squared to the minus 1. Now if you didn't do that minus 1 manipulation, it still works. And we had dx. So what we want is we want the dx to be in terms of dw. So the question is, how do you get a relationship between dw and dx? Differentiate. So we'll differentiate this. You go into the tables and the derivative inverse tan is in there. It's 1 over 1 squared plus x squared. In other words, 1 over 1 plus x squared. We are trying to solve this for dx. Actually, the other thing I can say is, as w substitutions go, this one's nasty. Okay. Right. So we want to solve for dx, so I'm going to multiply both sides by dx and multiply both sides by 1 plus x squared. I will get to 1 plus x squared times dw, oh that was, okay, equal to dx. So both sides by dx, it'll be gone here, 1 by dx is dx, multiply both sides by 1 plus x squared, 1 plus x squared divided by 1 plus x squared, it's gone, and I have 1 plus x squared times dw. So the dx that was here is equal to 1 plus x squared times dw. And this is the thing where actually if you didn't do the -1 you'd be in better nick here. Now I'm going to write this one kind of abstractly just above. So this is like something to the power of -1 times that something. And the question is, what do you get? So I can do it like 3 ways. I'll do the easy way, I'll just write down the answer here, we'll look at 2 more ways. So the easiest way, so what do we say to the power of -1 is the same